Hello all, I'm wanting to take up some of the homework from last night and start into the last topic in chapter 3, which is talking about hydrocarbons and some of the additional things. So we know that a hydrocarbon is a compound that contains only hydrogen and carbon, but that in reality that's not the only type of organic compounds, so we need to look at some of the other classes or families of organic compounds. Now, the homework from last night was on page 110. It's these questions here, and the first question is basically, what is a hydrocarbon? Like I just said, they're compounds that contain only hydrogen and carbon. Question 2 says, how are alkanes different from alkenes and different from alkynes? Remember, an alkane has only carbon-carbon single bonds, so I could have CH3 single bonded to CH3. That would be ethane, and we know that it's an alkane because there's only a single bond here between carbon and carbon. If I want to look at an alkene, I could look at CH2 double bonded to CH2, and boy, this stylus is giving me issues already. What I'm seeing is a double bond between the two carbons, and because each carbon has two bonds to the next carbon, it needs two hydrogens, so it's CH2CH2. And then the last one, an alkyne, would have a triple bond between the carbons, and that there would be a hydrogen coupled to this carbon, and a hydrogen, sometimes we actually write them in front, coupled to this carbon. So each carbon has four bonds, 3 to the next carbon and 1 to hydrogen, and that's an alkyne. So most of these compounds contain carbon-carbon single bonds, but then every once in a while we're going to add one or more double or triple bonds to our compounds. So question 3 here now is asking us to start drawing formulas for different compounds, and given what we already know from the C1 to C10, we should understand what meth, eth, prop, but, penta are going to do in the naming, and then how the endings, anes, enes, and ines are going to affect the structure with single and double and triple bonds. Now, if we start with butane, butane we know has got 4 carbons. Oh my goodness. It's got 4 carbons. 1, 2, 3, 4 carbons, and that each one is butane, so there are single bonds that join each of the carbons to the next carbon. And then the hydrogens needed to be added in. So this carbon has 1 bond to carbon, it needs 3 hydrogens, CH2, CH2, and CH3. All right, so there's butane. If I look at oct-2-ene, I'm seeing oct, which is 8 carbons. 1, 2, 3, 4, 5, 6, 7, 8 carbons. After the second carbon is my ene. So after the second carbon here, I need to not have a blob, I need to have a double bond. So there's my double bond between those 2 carbons, and then all the rest of them need to be flooded with hydrogens. So I'm going to have CH3 here. This second carbon has 3 bonds associated with it right now, 1 on this side and 2 on the right, so it needs 1 more hydrogen. This one, the third one, needs a hydrogen. The fourth one needs 2 hydrogens. Hopefully you're understanding why each carbon has the number of hydrogens that it has, and that is oct-2-ene. A bit messy, but it's oct-2-ene. If I move down to propyne, I'm seeing pro, which means 3 carbons, and ine means a triple bond. So I'm going to have a carbon, I'm going to have a triple bond to the second carbon, and then a third carbon. Remember, I'm not needing a 1 here because it doesn't matter whether the triple bond is on this side or on this side, it will both be prop 1-ine. And again, remember, chemists are a bit lazy, so if we don't have to write something down, we don't usually. So this first carbon needs a hydrogen because it has 3 other bonds. This second carbon here needs no hydrogens because it has 4 bonds already. And then the last carbon needs its 3 hydrogens to make it 4 bonds. So there's propyne. Now if I look at 4-ethyl nonane, okay, nonane means 9 carbons. So I'm going to make this a bit bigger here so I can have a bit more room to write. So 9 carbons, 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's my 9 carbons. I'm seeing, so there's nonane. So again, hide the prefix and just look at the nonane. So there's nonane, 9 carbons. And then I have a 4-ethyl to add to it. So on the 1, 2, 3, 4th carbon, I need to add ethyl. I need to add a 2-carbon group. So I'm going to add CH2, CH3 here. There's my ethyl group, which is added to my nonane. And then I need to put in all the rest of my hydrogens. CH3, CH2, CH2, CH, because this carbon already has 3 bonds. CH2, 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 CH3. Okay, and that makes 4-ethyl nonane. And then lastly, I have to draw that 3-methyl pent-2-ene. So I'm going to erase these ones up here. So you've got the video, so you can always go back and look at the answers that I've already done, or pause it and just go back to where. So I'm looking at 3-methyl pent-2-ene. So let's start, ignore the prefix, pent-2-ene. Pent-2-ene, 5 carbons with a double bond after the second one. So 5 carbons, 1, 2, 3, 4, 5. There's pent. 2-ene. I've got the double bond after the second carbon. And then I need a 3-methyl now. Okay, so I've done the pent-2-ene. Now I need to add in the 3-methyl. So on the 1, 2, I've got to count from the same end. So if I counted this side for 1, 2 to make the pent-2-ene, I always count so that the double bond gets the lowest number possible. So I've started counting from this end, so that's 2, and now this one becomes 3, so I need my 3-methyl group to go on there. There's my CH3 methyl group. And once my CH3 group's in, I can add the rest of my hydrogens now. This one becomes CH3. This one is CH. This next carbon needs no hydrogens because it already has 2, 3, 4 bonds, so it's done. This next one needs 2 hydrogens, and the last one needs 3 hydrogens. All right, so I'm always looking out to make sure that I've got my 4 bonds and everything. Okay, so there's 3-methyl pent-2-ene. Now, if I want to go down to the question 4 there, and I want to name the structures that are given for me. All right, so if I look at the first one is just going to be nice and easy. 2 carbons, which makes it eth. And I've got a double bond, ethene. I don't need to call it eth1-ene because it has to be 1-ene. There are no other options for this molecule. So because there's no eth2-ene, because it can't come after the second carbon, there really is only the 1 carbon there that I can be using. So I'm going to stick to just that one ethene, or eth1-ene if you wanted to, but eth1-ene is usually redundant. The next one has 4 carbons with no double bonds or triple bonds. 4 carbons is bute. Because they're all single bonds, it's butane. If I move down to C, I'm seeing 1, 2, 3, 4, 5, 6 carbons, which makes it hex. And the triple bond is, if depends if I count from this end, it's after the 1, 2, 3, or if I go from this end, it's after the 1, 2, 3. So it's hex, and then I've got an ine after the 3 carbon. Hex, 3, goodness me, ine, Y-N-E. Okay, so let's see if I can switch to my other stylus here. Maybe I'll have more luck. So hex 3 ine. Let's move down to the next one for D. So the trick here is I need to make sure I've got the longest continuous chain. Sometimes that can be tricky, right? So if I count from here, I've got 1, 2, 3, 4, 5. So if I count any other direction, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, I can only get 5 carbons, so I know it's going to be pentane. Okay, I know it's going to be pentane. So I have now named everything above the box there. But I also need to include this, it's 2 carbons, so it's ethyl pentane. And where is the ethyl? It's on the 1, 2, 3rd carbon from either end. So it's going to be 3 ethyl pentane. 3 ethyl pentane. Again, notice the dash between the 3 and the ethyl. Right. And then the ethyl pentane being one word. Let's scroll down to E. Okay, so E, they're trying to trick you up a little bit. Again, remember I have to have the longest chain that contains the double bond or the triple bond. Okay, so in this case, I have to include the double bond. So if I have to, it's going to be 1, 2, 3, 4 or 1, 2, 3, 4. So it's going to be a 4 carbon chain. And if I say, where is the double bond? If I count from this end, it's after the 2nd carbon. If I count from this end, it's after the 2nd carbon. So I know that it's going to be 1, 2, 3, 4 but 2-ene. But 2-ene. I also have to, so now I've named, now I've named this much, right? The but 2-ene, and now I need to include, there's a methyl group. There's a 1 carbon alkyl group that I'm going to add to my chain. So it's methyl but 2-ene. Methyl but 2-ene, and the question is, where is the methyl? Well, if I count from this end to make it 2, that makes the methyl on the 2 carbon. If I count from this end, the methyl goes on the 3 carbon, so I'm going to make it 2-methyl but 2-ene. Okay, and there's E. So notice that molecule there contains a lot of the things we've been talking about. It contains the double bond, the alkene. It contains an alkyl side group. We've got a number where the double bond is, number where the side group is. Right, so there's a lot in that question. If I go over to question 5 here, it says there's a model here of C2H6. So what type of model is this? We didn't get into the different types of models because we didn't get to build them. This is called a ball and stick model. And what I've got here is a carbon on this side with 3 hydrogens. Carbon is black, the hydrogens are white. There's a bond which connects the 2 carbons, and then the carbon with its 3 bonds. So what that molecule is CH3. CH3. Right, so we know that it is, that's ethane. Ethane. Okay, so it says, what information does this type of molecule provide? Typically, it just shows us the overall 3-dimensional shape. It tells me a lot more than this thing over here, right? This is useful. It tells me how many carbons, how many bonds, how many hydrogens are on each carbon. This shows me what it actually looks like. Where are the atoms, right? So it's actually better than just a a two-dimensional CH3CH3. It's a three-dimensional structure that shows shape. So C says what is the name of the compound? We've already named it as ethane. And D says draw the structural formula. We're not going to get into line formulas or anything else. I'm just going to go with CH3-CH3. Okay, question 6 goes into yesterday's note. It says place these following molecules. Place these following molecules in order from lowest boiling point to highest boiling point. Now from yesterday's note, we know that hydrocarbons that have the smallest number of carbons have the lowest boiling points. And those with the largest number of carbons have the highest boiling points. So to place them in order, I know CH4 is less than C4H10. H10, sorry for my writing, which has a lower boiling point than C12H26. This is why, because we know that smaller molecules have less attraction for their neighbors. We saw this in that video that I tried to add to my video, which I won't do ever again. A learning process, right? So because the CH4s have little attraction for their neighbors, they boil very easily. The C12 one is a huge molecule, so it has a big attraction to its neighbor. It holds onto its neighbors very tightly, and in order to boil, in order to change into a gas, it's got to let go of its neighbors, but it doesn't want to. So I've got to actually add a lot more energy. I've got to heat it a lot higher, and it's going to have a higher boiling point. Okay, question 7 here. It says a student has named this 2-methyl-but-3-ine. Why is this correct? It's correct for a lot of reasons. Okay, it's incorrect because number 1, there's no ine. It's an ene. It's a double bond, not a triple bond. Secondly, they've numbered it so that I've got 1, 2, 3, 4, so it is but. But if I count from this end, it's but-1-ene. If I count from this end, it's but-3-ene. So I want to count from the end which is lower, not this end, but from this end. So the name is actually going to be but-1-ene. So I have now named that but-1-ene. Oh, but now I need to add that. I'm going to add that methyl group, which is on the 1, 2, 3 carbon. I have a methyl group. So it becomes 3 methyl but-1-ene. Okay, that's the right name. They called it 2-methyl-but-3-ine, which is really far from where the right answer is. Question 8 says name a hydrocarbon that you rely on. Is it a gas, liquid, or solid at room temperature? So again, from yesterday's video, we saw lots of different examples. Maybe you use gasoline for a car, which would be a liquid. It contains methane, it contains pentane, hexane, and heptane. Again, I wouldn't expect you to remember that. You might use propane for a barbecue, which is a gas at room temperature. You might have driven on a road which is made of asphalt or tar. That would be a solid at room temperature. Those are very large hydrocarbon molecules. So again, we use hydrocarbons all the time. Most of your clothes are hydrocarbon. Are organic compounds, but they contain a lot of hydrocarbon bits. Right? So you're going to see as we move through this, organic is just everywhere. And then question 9, again, right back to yesterday's video, yesterday's note, it says crude oil is a mixture of hydrocarbons. Remember, the mixture is useless. I need to separate the components of the mixture so I can use each of the components for what I'm going to use it for. So it says what property is used to separate the different parts in crude oil, and the property is boiling point. Right? So as I heat the whole thing up, everything turns to a gas, and then as I cool it, as it goes up the distillation tower, the fractional distillation tower, as it moves into cooler and cooler and cooler chambers, it will slowly condense back into a liquid and be collected in each of the chambers as it moves up. And I'm not going to ask you to draw a sketch. I just want you to have an idea of how it works. And again, if we just kind of go back to our picture from yesterday, again, notice that our petroleum is coming in on this side here. Some of it is going to escape down here. Right, that's the heavy carbons, probably a liquid. We never even got it to the gas state. And then as the gas goes up the tower, it's going to cool. And then at each one, as some of it turns back into a liquid, the liquids will be collected, right, at the appropriate temperatures. And then at the very top, we can see that the lightest gases will actually go to the top, and we'll collect them as gases at the very top. The methane, ethane, propane, and butane, right? C1 to C4. Okay, so that's everything that we've talked about so far in that little review that we've just done in the last 20 minutes or so, or 25 minutes. Now, I want to spend some time now and move into our next section, which is 3.7. Now, I would normally have not taken up all that homework, but I forgot to book us a time for a live class this week. And I figure maybe we can just get away with, for this week anyway, because the ISU came in the middle of the week and it's taken up a big chunk of our week. We won't have a live class this week. We'll come back and have a live class probably Tuesday next week. All right, so 3.7. Okay, 3.7 talks about functional groups. Functional groups are atoms or clusters of atoms that are not hydrogen and carbon. Right? Remember everything we've done so far: methyl, propane, ethyl, 2-ethyl, heptane. Right? So as we worked through, everything that so far have been hydrocarbons. But it turns out that in biology, in the real world, a lot of hydrocarbons contain other elements. So some of the simpler ones are when I put a halogen. Halogens, remember, are chlorine, bromine, iodine, fluorine. If I add one of these elements onto my hydrocarbon chain here, somewhere along the chain, instead of having H's all the way around, if I put a halogen there, it becomes a haloalkane. Either a chloroalkane, a bromoalkane, right, an iodoalkane, or a fluoroalkane. Right. So the example they've given us there is methane, 1 carbon. There's my 1 carbon there, methane, and I've got a chlorine added to it, which makes it chloromethane. So there's one of the functional groups. These are the functional groups, right? And these are the families or the hydrocarbon derivatives that we're going to be talking about. Probably one of the most important ones in all of organic chemistry are a group of hydrocarbon derivatives called alcohols. Now, when I say alcohols, there's thousands of different types of alcohols in the world. Now, when I'm thinking about different types of alcohols, I'm not thinking beer, wine, vodka, scotch, whiskey, rum. I'm thinking all of those that I just said are one type of alcohol, right? They are ethanol. They are a 2-carbon ethane with an OH group added to one of the 2 carbons. Now, it turns out that there's a lot of other alcohols. All alcohols, as it turns out, are poisonous. Even the one that's in alcohol that we drink, that some people drink, is poisonous, which is why when a person drinks too much, we send them to the hospital and we say this person has alcohol poisoning. You think, well, why would a person be poisoned by something that everybody drinks or something that a lot of people drink? And it turns out, well, alcohol is poisonous. But when we drink it in small amounts, it doesn't kill us, it just messes with our brain, right? Enough of it will surely kill you. You can die from alcohol toxicity, from alcohol poisoning, right? When you have too much of it in your body rejects it, and you start throwing it back up. You say, I don't want to puke. Well, that's too bad. Your body's saying you've got this poison in your body, and we're going to do what we have to do to get rid of it. And you say, no, I don't want to do that, and then blah, it's all over the couch or all over the carpet. So all alcohols, it turns out, are poisonous. The one that most people drink is ethanol. All other ones are alcohols you would never want to drink. Right? They would get into your body, and they can cause major, major damage to your organs. And there's a lot of different alcohols. So one of the alcohols, sometimes it's called wood alcohol. It's this one here. Again, I can see that there's a CH3, which should be one carbon, which would be methane. And because it's an alcohol, we change the ending of the name to all. We're not going to go through all the naming of these things, but there's an example of an alcohol, and it's methanol. And again, remember the one that is typically in vodka, whiskey, rum, beer, wine, etc., all those things that people drink, is CH3, CH2, OH. So it's got the OH, the hydroxyl group, right? So this is the hydroxyl group. Before I added a halogen. Now I'm adding an OH, a hydroxyl group. Remember on our periodic table, I've put the polyatomic ions, and one of them is hydroxide, which is OH minus. This is a hydroxyl group. The O is actually going to covalently bond to carbon. It's not going to form an ion, which is hydroxide. It will covalently bond. And then this one that I've drawn here, CH3CH2OH, is actually ethanol. Okay, the all tells me that there's an OH on it, and the ethane tells me that there are 2 carbons in the chain. So there's my second functional group. My third functional group are compounds that contain a carbon that has a double bond to oxygen. Now, I'm going to switch to my whiteboard here, and I want to look at how this is going to happen. So we know that carbon has got its 4 valence electrons. Okay, and oxygen, I'm going to put oxygen up here. Oxygen has 1, 2, 3, 4, 5, 6. So it has 6 valence electrons. Right? It's number 8 on the periodic table, oxygen. So it has 2 and 6. Now, what's going to happen with carbon and oxygen is either the carbon, like the alcohols we just looked at, I'm going to make this just a bit bigger. The carbons are actually, the oxygen is going to form a bond with hydrogen and form a bond with carbon here. Right? And that would make an OH group. You can see that oxygen is now happy because it's got 2, 4, 6, 8 electrons around it. The hydrogen's happy, it's got its 2 electrons. The carbon has got its 3 other electrons that it's going to bond to other things, but it's taking one of its electrons to bond with oxygen to make the alcohol group. Now, what can also happen is the carbon, let's just slide this up just a little bit. The carbon can take 2 of its valence electrons to share with oxygen. So oxygen has its 6 valence electrons, right? Remember, oxygen's 8, 2 plus 6. So the 6 electrons are 2 here, 2 here, and 2 here. Those are oxygen's 6 electrons. Carbon comes along, and carbon is going to share 2 of its electrons back with oxygen to make that double bond. Right? Notice that oxygen is now happy. Oxygen has 2, 4, 6, 8 electrons, so oxygen is happy. Carbon is using 2 of its electrons here, so carbon still has 1 more electron to bond and another electron that it can bond with. So this molecule here, or this functional group here, is called a carbonyl. and it happens when carbon forms a double bond with oxygen, when carbon is sharing its other electrons with adjacent carbons. So I end up with a C double bond O in the middle of the chain, right? And that's called a carbonyl. So if I go back to my picture here, you can see here's the carbonyl. There's the carbonyl, and it's C double bond O, where the carbon is bonded to carbons on both sides. Now, if that's the case, then the molecule becomes something called a ketone. Ketones are things that you might have heard about, especially if you have any conversations or have had any conversations with a person who's diabetic. They need to be very careful about how they manage their diabetes, because if it's not controlled, they can end up in a situation called ketoacidosis, where their breath smells very, very sweet. That smell is a very bad sign for the diabetic person, because their body is in a pretty bad way, and they could end up basically calling 911, and it could end up with a very difficult situation. So ketones, their ending ends with -one, and because it's a ketone, and you can see there's a C double bond O in the middle of the molecule, and it's propanone. Propane, 1, 2, 3 carbons, with an -one, a ketone group, in the middle. Now, if it turns out that this C double bond O is on the end carbon, at the end of a chain, look at this example over here. There's my ethane chain, my 2-carbon chain. There's the C double bond O carbonyl group, and then the carbon is sharing its last electron with hydrogen. This molecule here is called an aldehyde. And again, aldehydes have very, very strong smells. They're used for a lot of different industrial processes. And one example is ethanal, which is the one that's there. You can see the ending ends with al, which tells me that the molecule is an aldehyde, and that it's ethane, 2 carbons there, with the aldehyde at the end. Okay, ethanal. Okay, my next group is also a carbonyl-based structure. I've still got my C double bond O like I had up here, right? But now that carbon is attached also to an alcohol hydroxyl group on the end. So the carbon here is bonded to the C double bond O, and it's also bonded to a second oxygen, which is coupled to a hydrogen. And then the carbon that's in that position will also be coupled to the rest of the chain, whatever the rest of the chain is here. They've made it just a 2-carbon chain, ethane, and then it's a carboxylic acid. So the ending of this name is that it's an ethane-based acid called ethanoic acid. And again, you're not going to need to know how to do these. Just recognize that there's that possibility also. Okay, we've got another possibility here where we have a compound called an ester. Esters are very, very common from a lot of plant-based products, things that smell very, very strong. Think about the smell of certain flowers, lilacs or roses. Think about the smell of certain types of fruit. Again, if I had a pineapple in my classroom and I carved up that pineapple, there was nobody in the room, and you're all outside the door waiting, and I didn't notice the door was locked, without even seeing me carving up that pineapple, a bunch of you would say, "I smell pineapple. Someone's eating pineapple." Or if I had some really citrusy oranges and I was cutting oranges up, you all walked into the room now, someone goes, "Oh, someone's been eating oranges, I can smell." Right? Those are esters. They're very, very strong smells, very characteristic smells, sometimes very nice smells, sometimes very not so nice smells. It can be really horrible. Most of the esters, actually, I shouldn't say that, most of the esters actually smell very, very nice. And the structure of an ester, so again, look at the structure here. Now, it's not going to be important that you remember all these structures. It's important that you see how they're built, right? Because at the end of the day, we're going to be talking a little bit more about these different types of families or hydrocarbon derivatives, because we need to understand how they're used for different industrial or regular chemical processes. So there's your ester bond. The family are called esters. And then you can see that the one carbon here has double bonded to oxygen. It's bonded to a second oxygen, and this second oxygen isn't bonded to hydrogen like I had up here, like I had with the alcohols further up here. The oxygen is going to share its second bondable electron with another carbon, and what that makes this structure here, C double bond O, with more hydrocarbons on this side, makes it an ester. Right? And these are, again, if we were in school, one of the labs that we like to do is to make aspirin. Aspirin is an ester. Doesn't smell very much, but it is an ester, and it's one of the esters that we typically like to make in school. Okay, the last two groups contain nitrogen. One of them contains the carbon, hydrocarbon group. On the end of one of the carbons, instead of having a hydrogen there, there's going to be a nitrogen there. Nitrogen is number 7 on the periodic table. So it's got 2 and 1, 2, 3, 4, 5 electrons. So to draw a Lewis dot diagram for nitrogen, 1, 2, 3, 4, 5, right? And what can often happen is 3 other atoms will typically bond to the 3 electrons that are around nitrogen. A very common molecule in the world is NH3, where the nitrogen shares 1 electron with hydrogen, shares a second electron with a second hydrogen, shares a third electron with a third hydrogen. And notice now that the nitrogen has 8 electrons around it, making it happy, making it stable. And the hydrogens all have their 2, and they are stable also. So again, to draw this as those are the 2 non-bonding electrons. Then I have NH, NH, and NH. That's ammonia, NH3. Right? And it forms because of the 3 valence electrons that are bonding electrons on nitrogen. So nitrogen always wants to form 3 bonds. Just like carbon always wants to form 4, oxygen always wants to form 2, nitrogen always wants to form 3. Okay, again, let's do carbon again. There's carbon with its 4 valence electrons, so it wants to form 4 bonds. Here's nitrogen with its 5 valence electrons, so it wants to form 3 bonds with those 3 bottom electrons. And then oxygen is 8, so it's got 2 in the first row and then 6 in the second shell, right? And it wants to form 2 bonds with these 2 electrons. Nitrogen forms 3 bonds, carbon forms 4 bonds. So nitrogen will always want to form 3 bonds. Now let's go back to our note. In the note here, you can see that the nitrogen down here has 3 bonds around it. One of them connects to carbon. The other 2 can connect either to hydrogens or to other hydrocarbons. Okay, that makes a family called the amines. Called the amines or amines. And they have, you can see here that the CH3NH2, carbon has 3 hydrogens and a bond to nitrogen. Nitrogen is bonding 1 to the carbon and 2 to hydrogen, so nitrogen has its 3 bonds. Okay, and there's the molecule there. So it's got an NH2. And then the very last group, again, if you take biology, we talk about a group of chemicals in biology called proteins. Proteins are the machinery of life. And to build proteins, we need to form a chemical bond called an amide bond. The amide bond is this one here. It's the one that holds amino acids together. And at the end of the day, what's happening is I've got a carbonyl group, which is this C double bond O here. So carbon is bonding 2 to oxygen, which is making a double bond. Carbon's going to share one more of its electrons with nitrogen, and then the other electron on the left side here with either a hydrogen or more of a hydrocarbon chain. You can see an example here. Carbon is double bonded to oxygen, bonded to nitrogen, which in this case has 2 hydrogens. Remember, nitrogen needs 3 bonds. 1, 2, 3. Carbon needs 4. 1, 2, 3, 4. And this carbon has its 4 electrons, 3 to hydrogen and 1 to carbon. These molecules have the special name of amide, and amides always have the carbonyl, C double bond O, and then they have a nitrogen also bonded to that carbon. So these are all the different families. This is organic chemistry right in front of you here. We could spend an entire month learning about these different families, these different hydrocarbon derivatives, learning how to name them, how to talk about them, how to draw them, and then ultimately perhaps even how to build them, right? Chemical reactions that we can use to make some of these things, right? So that's all the functional groups. If I go back to my note, that's not the note I want. If I go back to my note from yesterday, okay, so when I talk about functional groups, I'm talking about the fact that there are just so many different types of organic compounds, and that we try to group them into families, and that there's a number of different families, right? We talked about alkyl side chains, such as methyl, ethyl, propyl, butyl, and then we talked today about side chains that are not just hydrocarbons, but we talked about ones that involve oxygen. Here's our oxygen here with its 6 valence electrons, and nitrogen with its 5 valence electrons, right? So nitrogen wants to form 3 bonds, and oxygen will always form 2 bonds, just like carbon always forms 4 bonds. And then in the note that I've created, you can see alcohols here have got the hydrocarbon chain. I've got the CH3 group here, CH2, 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 and then an OH, and the OH makes it an alcohol. I've got another one here where I've got the CH3 group, CH, CH2, CH2, CH3. This one that has a CH is taking the other electron and bonding it to oxygen, and oxygen's bonding also to another hydrogen. That makes it an alcohol also. Right, so there's a lot of these different alcohols, and like I said, ultimately they have a huge number of different applications in organic chemistry. We talked about aldehydes and ketones, which are the molecules that contain the carbonyl group. If the carbonyl group is at the end of a molecule, it makes it an aldehyde. So I've got the C double bond O, and the carbon is attached to a terminal hydrogen. If the carbonyl group is attached somewhere along the middle of the chain, so there's my carbonyl group again, right? And you can see that these are ketones, right? They're ketones, which means they've got a carbonyl group in the middle of the chain. I've got propanone and butanone. Propanone is got the common name acetone, just like dihydrogen monoxide is water. Propanone is got a common name of acetone. And like I said, typically the ketones have a very strong, sometimes very sweet smell. Sometimes they make things smell nice. Again, think about the smell of gasoline. Some people love that smell. Some people hate that smell. But ultimately, we all know that smell, right? It's because of the compounds, the organic compounds that are in there. There are carboxylic acids. The carboxylic acids have a C double bond O and an OH on them, right? And that makes it a carboxylic acid. C double bond O and an OH on the terminal carbon makes it a carboxylic acid. This carboxylic acid is called lactic acid. It's the one that people can have reactions to. If we say that you're lactic acid intolerant, then lactose intolerant, you have a hard time dealing with some of the metabolites of lactose. Methanoic acid is an acid that's the acid that's produced by ants that cause stinging ants when they bite you, and other insects making their methanoic acid. We have the esters. The esters, again, contain the C double bond O and then the CO. And then I've got a hydrocarbon chain on this side and more hydrocarbon chain on this side. A lot of very strong smells, a lot of very nice smells. So the smell of pineapple, the smell of peaches, the smell of berries, right, are all because of esters. If we keep on going, the last groups are the ones that contain nitrogen, and those are the amines. So here's an amine right here. They often have very strong smells. Here's the NH2 coupled to carbon. Here's another NH2 on the same molecule coupled to carbon. This particular compound is called putrescine, which probably gives you a clue about what it smells like. It smells like rotting meat, and it is a very revolting, horrible smell. Most of these compounds have got what we would kind of become to know as a nitrogen-y smell or an ammonia kind of smell, and that's what you often find in different types of cleaners, like window cleaner, Windex, etc. You also find that in the smell of fish that maybe isn't so fresh. You bought fish at the store and you get it home and you go, "Wow, that fish smells really fishy." Whereas sometimes you get fresh fish and it doesn't smell like that at all. And the difference is how much of the amine has been produced in the molecule. And then the last group that we talked about today are the amides. The amides are the ones that have got a C double bond O and the carbon is bonded to nitrogen. And then I can have a hydrocarbon on this side of the nitrogen and more hydrocarbon on the left side of the carbonyl group of the C double bond O. Okay, this is a lot. Like this is, I don't pretend that this isn't a lot today. This is a lot. So I encourage you to go back and spend some time looking at the notes that we've talked about for the different functional groups. The last one here is the first one that was actually in the chart. Those are the haloalkanes. Those are alkanes that have got a halogen on them, either chlorine, bromine, or iodine. And when those are added to our halogens, these compounds basically never existed on Earth. Right? 50 years ago, there were no haloalkanes anywhere on this planet. And then humans came along and discovered these molecules that we could make. And when we did, we discovered that they are useful for lots of things. They're useful for killing bugs. They are useful in refrigerators and air conditioning units. They are useful for the production of a lot of different types of synthetic materials, including plastics and styrofoam. So when we started making these things, we thought, this is terrific. We've discovered this new type of chemical that never existed before, and we're going to use it to make all this stuff. And we now know part of the problem that we're seeing in the world today is because of the chemicals we're producing that were never here before. Again, there was no plastic on Earth before 1950, right? And let's look at how much plastic there is surrounding you wherever you're sitting right now. I'm sitting at my desk. I've got a plastic cup on my desk. I've got a keyboard for my laptop. A lot of my laptop is plastic. My mouse is plastic. My marker for my whiteboard is plastic. The coating on the whiteboard is plastic. The cord that's plugging my laptop in right now is basically plastic. I mean, I don't have to look too far from where I'm sitting. If I close my eyes and just move my hands around where I'm sitting, all I'm going to touch is plastic, really. All right, so again, there was no plastic before 1950, and now it's everywhere. So we are discovering that some of these haloalkanes and some of the organic compounds that we're producing are maybe not so good. And as time goes by, we're going to have to find better ways of producing things that we want, because a lot of these things are really dangerous. Okay, so I'm going to stop there. I'm going to ask you to go back and read through my note again. Look at these structures. Look at table 3.6 in the textbook. So this is table 3.6 here. Those are all the functional groups. And just have a quick look at the different, there are 3, 4, 5, 6, 7 groups. Haloalkanes, alcohols, ketones and aldehydes, carboxylic acids and esters, amines and amides. There's actually 8. There's 8 different hydrocarbon derivatives. Just recognize what it is that makes a molecule. What is a carboxylic acid? It's got a C double bond O bond OH. All right. Now, you may want to. For now, I'm just going to encourage you to read through that one page. It's really all it is in the textbook, and then read through my note. And then I'm going to come back. So that's section 3.7. I was going to try and do 3.7, 3.8, and 3.9 all together, but I've been going hard at this for the last almost hour now. I want to stop. Okay, so encourage you to go through that. Make sure that you've done the review. That was the one that I did the homework. I took up all that homework at the beginning of this note, and we will come back to this. It's Thursday now when you're looking at this, so maybe Friday I'll finish this note up, and then we'll be done chapter 3. I'm not going to test you on chapter 3. I'm going to add it to chapter 4, because if chapter 4 is a short chapter, just like chapter 3, we started 2 days ago, and we'll have one test for organic chemistry, and